Okay, so here in 7.3, we're going to start looking at solving exponential equations, okay? So at this point, how we algebraically solve exponential equations is actually through logarithms, which we haven't learned yet. But for now, we are going to look at a couple other strategies we have in terms of solving exponential equations, where we're solving for x, we're solving for that variable that's in the exponent. So one of these methods we're going to look at is, obviously you can do it graphically and estimate it from the graph. Another way that we're going to look at is the change of base method, right? And you might remember this, seeing it in Pre-Cal 11 when we did sequences and series with geometrics, okay? So the point of this is to really make sure you're brushed up on your exponent skills, okay? So when you're talking about rewriting things as base of 3 in this example, you're looking at, okay, how can I rewrite 27 so that it still has a value of 27, but instead it's 3 to the power of something, right? And this one should be fairly common, such that 27 is equal to 3 cubed, okay? So that's what we're going to look at first. So 27 is actually equal to 3 cubed. All right, so in B, we've got 9 squared. So I want to rewrite 9 squared as 3 to the power of something. Now we can do this in two ways. The first way is you can actually evaluate 9 squared first, realize that that is 81, and then realize that 81 can be rewritten as 3 to the power of 4. Okay. The other way of doing that, if you maybe didn't know that 81 was 3 to the power of 4, is instead looking at 9. Okay. 9 is pretty common, and you should already know that 9 is equal to 3 squared, so we can rewrite 9 as 3 squared, but then that value is being squared. Okay? And from there, you're using power of a power law with exponents, where you've got 3 to the power of exponent, which is then taken to another exponent, which means you multiply those exponents together. So really, that's 3 to the power of 2 times 2, which is 3 to the power of 4. All right? Then it gets a little bit more complex here in example C, where you have 27 to the power of 1/3 multiplied by the cube root of 81 all squared, right? And this again relies on your knowledge of exponents, okay, and your exponent laws. So again, 27 can be rewritten as 3 cubed, right? So that's 3 cubed to the power of 1/3. Okay? And again, power of a power there, 3 times a third is just 1. So really that's 3 to the power of 1. We can then look at the next portion, which is the cube root of 81 all squared. Right? And again, if you can remember your exponent laws of what happens when your exponent is a fraction, it turns it into a radical, where the denominator of that fraction becomes the root of your radical. So in this case, denominator would be 3. And then it's taken to the numerator, which in this case is 2. So we could rewrite this as 81 to the power of 2/3, right? Where that denominator of 3 relates to the cube root, and then the whole thing is being squared, so it's to the power of 2. Okay? And then from there, we can then rewrite 81 as 3 to the power of 4, right? So that's 3 to the power of 4 to the power of 2/3. Once again, recognize that as a power of a power. So we've got 3 to the power of 1 times 3 to the power of 4 times 2/3, which is 8/3. Okay? Yet another exponent law coming into play here. We've got two powers with the same base, each with base of 3 being multiplied together, and we add the exponents in that case. So that's now going to be 3 to the power of 1 plus 8/3, which is 11/3. Right? Because obviously 1 can be rewritten as 3 over 3, and then you're just adding fractions, right? And that would be your final answer there. So that's how we rewrite things in terms of a different base, okay? And how that's used in solving equations is that if we can change the base, and just kind of as a side note here, if we can have 4 to the power of x is equal to 4 to the power of 2, right? It's a very simple example. Well, what does that tell you about x? What can you conclude? Well, since they're equal and they have the same base, then the exponents have to be the same, right? And x would have to equal 2. And that's the property that we're using here. If we can get the bases on both sides of the equation to be the same, we can therefore set the exponents equal to each other and then solve, right? So in this case, you've got 4 to the power of x plus 2, okay? And 64 can be rewritten using change of base formula as 4 to the power of 3. So 64 is now being written as 4 to the power of 3, all to the power of x. Okay? So now what we have is 4 to the power of x plus 2 is equal to 4 to the power of 3x. And there we have it. We've got that situation there where we have a base, the same base on both sides, 4, and then it's to the power of x plus 2 and to the power of 3x. So since the bases are equal, we can therefore conclude that the exponents must be equal to each other as well, such that x plus 2 is equal to 3x. And this is now just a linear equation that we can quickly solve such that 2 is equal to 2x, and therefore x is equal to 1. Okay? We need the same thing here in b, except for we can't rewrite 8 as 4 to the power of something. However, we can take both of those and rewrite them as 2 to the power of something. So in that case, the 4 can be rewritten as 2 squared, then to the power of 2x, which is now equal to the 8, which can be rewritten as 2 cubed to the power of 2x minus 3. Right? Again, applying your power of a power law, 2 times 2x will be 4x, so it's 2 to the power of 4x. And make sure you're applying the distributive property here in that the 3 is being multiplied by the entire 2x minus 3. So that entire exponent now will be 6x minus 9, right? So it's 3 times 2x and then 3 times negative 3. Now you've got bases that are the same, that are equal to each other, which can therefore allow us to conclude that the exponents are equal. So 4x is equal to 6x minus 9, okay? And again, solving that, you get that 9 is equal to 2x, or that 9/2 is equal to x. Okay, so that's the change of base. So you're trying to get both sides the same base to the power of something equal to each other, so you can set the exponents equal to each other. Okay? Now, just looking at an example in which you might come across, a very common one dealing with exponential is that of compound interest. Okay? And this is the formula here that you can see. That is the compound interest formula. Okay? This A represents your future value, right? So what you're hoping to end up with. Okay? Your P value, that represents your principal amount, right? That's your initial amount that you've invested. Okay? The I value is your interest rate. Okay? But this is actually your interest rate divided by the number of compounding periods per year. So how often, how many times per year does the interest get added in how many times does the interest get added in per year? Okay? And then your end value is in fact your number of compounding periods total over the course of the investment. Okay, so just keep that in mind as we look at this problem. So Christina plans to buy a car. She has saved $5,000. The car she wants costs $5,900. How long will Christina have to invest her money in a term deposit that pays 6.12% per year, compounded quarterly, before she has enough to buy the car? So this is where we're basically trying to identify our values, right? So this compounded quarterly indicates that you're going to have the interest compounded 4 times that year. So that I value is going to be that interest rate, which is here at 6.12%, so that we're going to put that as a decimal as 0.0612, and we need to divide it by 4 because that interest happens 4 times, right? That 6% over the year happens 4 times, so we need to divide it by 4 to get the actual value there, okay? So that will give us an I value of 0.0153, all right? Our principal amount is the amount that we've already got saved up, invested. In this case, it is $5,000, okay? Our future value, right, we know we need $5,900 to buy that car, so that value is $5,900, and we're essentially solving for n, right? How many of those compounding periods is it going to be until she has enough money for the car? Okay, so in that sense, we start evaluating. Okay, so we've got our A value there at 5,900. We've got that P value at 5,000, and then 1 plus 0.0153 to the power of n, and we're solving for n. So there's 2 things we can do here. The first is divide both sides by 5,000. So we can do that 5,900 divided by 5,000. And that gives us 1.18. And we can add these 2 values that are inside the brackets here to be 1.0153 to the power of n. Okay? Now again, we don't have an algebraic way to do this that's, perfectly exact yet. But what we can do is apply that similar change of base. We are going to try and change 1.18 and rewrite it as 1.0153 to the power of something, so that way it can equal 1.0153 to the power of n. Okay, so we're going to have to just do that with a little bit of guess and check. Right, so you would just head to your calculator, 0.0153 to the power of, so let's say I try 7, that only gives me 1.11. If I do 1.0153 to the power of 10, that's 1.16. 1.0153 to the power of 11, 1.1817. All right, so that's my best bet there. Okay, so what we've got here then is we can rewrite that as 1.0153 to the power of 11 is equal to 1.0153 to the power of n, which therefore means that n is equal to 11. Okay, now that's not 11 years because n represents the number of compounding periods, and since it's compounded quarterly, we take that 11 and we divide it by 4 to get the number of years. So it's going to be 2.75 years until she has enough money for the car. Right, and that's assuming she doesn't put any more money in it, right? She just invests it and then it just sits, okay? So if it'll have to sit for 2.75 years before it accumulates to that $5,900, okay? Just one final example to look at. Again, you'll see a lot of these questions in terms of half-life. So in this case, you've got nickel 65. They're telling you it has a half-life of 2.5 hours, right? So again, going back to that initial lesson that we did, anything that has a half-life tells us that its ratio is going to be 1/2, okay? So to start with, I've got this mass is equal to 1/2 to the power of t, where t is time, right? But it's telling us that the half-life is 2.5 hours, which means it gets cut in half. The mass of nickel is cut in half every 2.5 hours. So that means I've got to apply that horizontal stretch like we talked about, and it's actually m is equal to 1/2 t divided by 2.5. Okay? There's nothing else that's happening, right? We would assume that the mass would approach 0 as it goes, so we don't have a vertical translation that we need to apply here. We haven't been given a value of an initial mass that we need to apply here, so this is our equation, okay? Part B is then using that equation where it says what fraction of a sample of nickel 65 will remain after 10 hours, right? Assuming that our initial sample is a whole, right, so 1, right, so if it helps, you can rewrite your function and kind of apply an a value of 1, right, talking about like 100% or 1 times 1/2 divided by 2.5, right, but now we're asked how much it is after 10 hours. So t representing time gives us the opportunity to just evaluate this as 10 divided by 2.5. So 10 divided by 2.5 is 4. So it's 1/2 to the power of 4, and again, what that's going to be, your mass is now going to be 1/16, right, which is 1 to the power of 4 is 1, and 2 to the power of 4 is 16. So it's the fraction that's left after 10 hours is 1/16 is what's going to be left, okay? In C, we're kind of working backwards, right? So it's how long will it take for a sample of nickel 65 to decay to 1/1024th of its original mass? So that's actually a mass value there. So we can substitute that 1/1024 in for m, and that now equals that 1/2 to the power of t over 2.5. Right, and now we're solving for t. So this one can actually be used as a change of base method. Okay, if you've ever played that game 2048, you should notice that 1024 is one of those, exponents of 2. Right, it's 2 to the power, it's a power of 2. So even if you can't figure it out quickly, you can always just go back and guess and check, but it is in fact 2 to the power of 10, which means that this 1/1024 can be rewritten as 1/2 to the power of 10, which is equal to 1/2 to the power of t over 2.5. So this one can be done using change of base. So now you have the same base equal to each other, therefore we can make the conclusion that the exponents are equal and that 10 is equal to t divided by 2.5. Multiply both sides by 2.5 and you get 20.5 is equal to t. Okay, so that's going to mean, no you don't. You get 25. I'm dumb. Okay, so you get 25 is equal to t, right? So that gives you your 25 hours, right? So it's going to take 25 hours.
Would Xavier Coggins please come to the office? Xavier Coggins to the office, please. Thank you.
Okay, so 25 hours to decay to that 1/24th of that original, 1/1024th of its original mass. Okay, and again, trying some questions like that are here for you. Okay, and that's 7.3.